Hey, hello everyone, and welcome back to the 14th LISA Symposium. This is the parallel session on extreme mass ratio interspirals. I'm Jonathan Gehr from the Albert Einstein Institute in Germany, and I will be chairing this session. We have three talks before the break from Gabriele Piovano, Matteo Bonetti, and Xian Chen. We ask that people submit questions via the chat. You can submit questions at any time. If you do want to ask a question verbally, you can, but please raise your hand and we will answer all the questions at the end of each presentation. Those of you who are following through the live stream on YouTube are also welcome to ask questions. Okay, so we'll now move to our first speaker, who is Gabriele Piovano from the University of Rome La Sapienza, and he will be talking about love and EMRIs in SPA. Gabriele, please take it away.
Okay, perfect. Thanks, Jonathan, for the introduction, and thanks also to the organizer for allowing me to speak today. I'm Gabriele, postdoc in Rome, and today I'm going to present a recent work done in collaboration with with Andrea and Paolo, and it's all about EMRIs, log numbers, and the stationary phase approximation. First of all, probably it's maybe not necessary, but just to put all of you on the same page, I'm talking about special types of binary called EMRIs, which are given by the capture of a stellar massive object by a supermassive black hole. And why these binaries are important because of some of the primary targets for LISA. The properties of the binaries can be measured with excellent accuracy. And this may allow to do tests on gravity, on the structure of the components of the binary. And one of the effects that may allow us to distinguish, like, for instance, a supermassive black hole to a supermassive exotic compact objects are the tidal deformabilities. Under certain assumption, the response to tidal deformation on an object can be parameterized by what are called tidal log numbers. And for a black hole, the log numbers are exactly 0. So it's a bit more complicated, but say the tidal log numbers are exactly 0, while for exotic compact object may be very tiny, but different from 0. So the question we wanted to answer to this work is, can we measure the tidal log number, supermassive exotic object in EMRIs, and say something about its nature, if it's a black hole or not? In this work, we did a parameter estimation with a Fischer matrix approach, using what is called a stationary phase approximation, plus a few tricks to simplify our analysis. So in this talk, I will maybe say something about how to model the spiral. Well, we move on to the parameter estimation done with the Fischer matrix, the stationary phase approximation, and then I will draw some conclusions and future perspective. So, first of all, the two quantities, I don't know if you can see my cursor, but the two quantities that enter in the waveform are what are called the tidal deformabilities, which are λ1 and λ2 of a primary, the supermassive object, and the secondary, the smaller object. And you can see that for the primary, the tidal deformability is proportional to the tidal log number, while for the secondary, this quantity is suppressed, λ2 is suppressed by the mass ratio Q. So it's practically impossible to see any effects, tidal log number to the secondary, but you can see some effects on the primary. And most importantly, these effects enter either leading order in the gravitational wave phase. So it's an adiabatic, it's called adiabatic effects. And we consider in this work circular equatorial orbits, and we include the effects due to the tidal lobe number of the binding energy and the fluxes through post-Newtonian terms at 6 p.m. order. And for modeling our spiral, we do the following approach. We consider the binding energy of a point particle, including the contribution of a secondary spin, which are given by these terms here, A0 and A1, where sigma is a small quantity suppressed by the mass ratio Q, with chi the spin of a secondary rescaled by the mass of the secondary. And for the fluxes, we consider Tsiolkovsky fluxes given by F linearizing the secondary spin sigma, including the contribution of the tidal lobe number with our post-Newtonian terms. The same also for binding energy. And with this expression for binding energy, the fluxes here, we have this evolution equation for the radial orbits and the gravitational wave phase. With this, equation here, we can now move on to a parameter estimation with the stationary phase approximation. So we, as I mentioned in the beginning, we did the analysis with what is called Fischer matrix approach. In the high signal to noise ratio, your likelihood, your probability distribution can be approximated by a Gaussian distribution, which is given by, where the covariance matrix is given by the inverse, what is called the Fischer matrix, which in turn given by the scalar products of the derivatives of your waveform. Here we have a sum of the two channels of laser, because under certain assumption we can assume that laser is like two different interferometers, and we sum the contribution given by these two channels. And here we consider 12 parameters for circular equatorial orbits with spin aligned or anti-aligned. We consider the masses, the spins of the primary and the secondary, the initial time, the tidal lobe numbers, and then some of the angles. In particular, this is a theta s, phi s, theta chi, gives the sky position and the position of the orbital angular momentum of the binary, and then we also consider the distance from the source. One of the problems of this approach is that the Fischer matrices are usually ill-conditioned. If you have a small numerical systematic error in your Fischer, which translates in large error in the covariant matrices. And some of the problem is due to the fact that these derivatives of the waveform are often computed like with the finite difference method. We found a way using the stationary phase approximation and some analytic trick to at least ameliorate the problem that you have in computing the numerical derivatives. So first of all, this is your approximation of the waveform in the frequency domain. We have all of these expressions here with taking into account also the motion on LISA and what's called the antenna pattern function F of the two channels, which are time-dependent quantities, and also the Doppler shifts due to the motion LISA. What's important here that maybe some of you will recognize this as one of the typical waveforms that they are now in textbook for the chirp of spiral circular, spiral binaries in circular equatorial orbits, with the important difference that you have this time tilde f, the orbital phase, and this the omega dot frequency here, which are known numerically, non-analytically. Using this expression here for the SPA, we found a way to compute this derivative of your waveform in a what's called semi-analytic fashion. And the way is as follows. You have the problem as given by, for the computation of the numerical derivatives by these intrinsic parameters here, the masses, the spin, and the tidal lobe number, which appears in an intrinsic way of your parameters here. So for the time tilde here, which is defined in this way here as a solution of the implicit function, this time till here, For the theorem of implicit function, we can define the derivatives in this way, while for the derivative of the orbital phase and the orbital radius, we can use this expression here, and the evolution of the derivatives of the wave from respect to our parameter alpha can be given by simply this expression here. We also did some checks to compare the stationary phase approximation with what is called the fast Fourier transform of your time domain signal. We first compute the faithfulness between the two signal, and we can see that even for a fast spinning, also another important thing, we consider any spiral deep down to the ISCO of a Kerr primary. And you can see that this faithfulness here is nicely close to 1. The closest this quantity is here to 1, the better, which means that the two waveforms we are comparing are equivalent in a way. We also did a more important check. We compare the standard deviation compute with the fast Fourier transform with the standard deviation compute with the stationary phase approximation with the same analytic derivative that I showed before, and we see that the standard deviations computed this way are equivalent. Say the error on your parameter. I will explain you in a moment what I mean for the prior of keywords. This is me just to say that the two methods, the stationary phase approximation FFT, are equivalent. So, all being said, can we measure now the Taylor number of the primary? The answer is yes. You can measure it with a very great accuracy. This is the log 10 of the errors, and we consider two cases when we impose a prior on without a prior on the spin of a secondary, which has a large error, so this quantity cannot be detected, but it has an impact on the other parameters. We also consider the case in which we impose a Gaussian priors on the secondary, which simply say that the spin of 7 is limited between -1 and +1. In any case, this is the error that we have for the Taylor number of the primary for 0.9 and 0.99. Here we have also the table for the sky localization of the source and the angular momentum. It's just to say that the Taylor number of the primary can be measured with great accuracy, and these have some consequences in the way in which you can probe some microscopic, or if you want, even Planckian corrections at the event horizon. Because for certain class of exotic compact objects, the distance between the event horizon of a Schwarzschild black hole and the surface of an exotic compact object scale in this way here. And so if you have an accuracy of this level to a Taylor log number of the primary, you can put some constraints on the distance between your exotic compact object and the surface of what would be a black hole at this level here. Still, you can put like some very nice constraints, even for mildly spinning primary, as you can see here, where you have like plot the error on the Taylor log number on the spin of a primary, and this constraint here can be like several order of magnitudes more stringent than what you have in measure of the Taylor log number for the first events with the merger of two neutron stars. But there are some caveats that I'll explain in a moment in the conclusions. So to sum up, we compute the error of the Taylor log number of supermassive object with EMRIs with a Fischer matrix approach, and using some the stationary phase approximation, some analytic tricks, let's say. The Taylor number with primary can be saved with very good accuracy. We may distinguish potentially the supermassive black hole in EMRIs from a separate class of echoes, but the relation that I showed before is technically valid for a certain class of exotic compact objects, non-spinning, and we neglected also, most importantly, important cell force effects. We consider simple orbits, and also we simply added a positive contribution Taylor number at the post-Newtonian level, assuming that is still valid in a strong regime. This is not should be a too dramatic approximation, but still an approximation. And I briefly conclude, say that some future work we consider more general orbits, eventually consider if possible other important effects and maybe test some probable deviation together with the title number. But the very last slides, I should upload soon all the code in this GitHub repository. This works as usual, the black hole perturbation toolkit, a fantastic toolkit for if you want to do black hole perturbation computation. And if you have any questions later, you can even send me an email at this address here. And thank you for your attention.
Thank you very much, Gabriele, for that nice talk. Are there any questions? Well, I can ask the first one. What would you think the effect of eccentricity will be to improve the strength of the measurement, or will it make it more complicated because it's likely to be degenerate?
Actually, I don't know. I would expect naively that it will deteriorate a bit the strength of the measurement just because you are adding more parameters in your analysis. So it's usually the more parameters you have, the less accurate you have can measure all of your parameters, especially the one that are dominant. But one should do the analysis to truly know the answer.
So are you planning to extend to eccentric and ultimately generic waveforms when they're available in the BHPT? I mean, do you know how you would add the tidal corrections in that case?
That's actually, I don't know exactly. Probably there are in the literature at least some expressions for maybe small eccentricity. I would say some PN expressions with small eccentricity. I didn't check actually. It's what would be a possible extension. Something that I would like to do is try to use the stationary phase approximation and extend it in the form more generic orbits in the same way as has been done in a paper by Scott Hughes and collaborators, and use that use their method with our method to compute the numerical derivatives and apply it to some parameter estimation. That would be interesting, at least for me.
Okay, thanks. There is a question in the chat from Danny Laghi, who's asking what the range of SNRs you analyzed for the EMRIs. Did you put them at different distances, or were they?
Let me just go. Here we consider as a distance 1 gigaparsec, and we scale all the SNR to an SNR of 30. Okay. But for this, the configuration here, you can have easily like a relatively high SNR, but to be conservative, we will scale to an SNR of 30.
Thanks. Are there any more questions? In that case, thank you again, Gabriele, and we'll move on to our second talk. So the second speaker today is Matteo Bonetti from the University of Milan Bicocca. He's going to be talking about EMRIs triggered by massive black hole binaries. Please, Matteo, when you're ready, take it away.
Thank you. So, hi everyone, I'm Matteo. I'm postdoc here at the University of Milan Bicocca, and in this talk I will present our recent work about the formation of extreme mass ratio spiral triggered by the presence of a massive black hole binary. This work has been done in collaboration with all the people listed here, and specifically this was the master project of two master students, Riccardo Colombo and Giovanni Mazzolari, that now has just started the PhD at the University of Bologna. So, what are EMRIs? As Gabriel was saying, EMRIs are binary systems with extreme, so very small mass ratio, and they are generally formed by compact objects, so black hole generally, but also neutron star and white dwarf for the stellar mass object, of course. And they are very important source of gravitational wave. So the classical example of EMRI is a binary system formed by a massive black hole that we can find at the center of galaxies, and a stellar mass black hole that is orbiting nearby. EMRI will be primary gravitational wave sources for the LISA sign case, and in fact we expect that many of them will shine in the most sensitive part of LISA, so here in the bucket. And so they will be very important, especially because the extreme mass ratio makes the gravitational wave emission extremely inefficient. And so this means that we can observe a quite long spiral, up to 10 to the 5 orbital cycle of this object. And so if we can track all this long spiral, we can perform extremely precise measurement and infer something about the source of gravitational waves. And so then we can perform tests. For example, we can precisely map the space-time around the massive black hole and maybe find out deviation from the Kerr metric. So we can do GR tests. We can test cosmology for the luminosity distance and also the redshift of the source. We can also analyze the nearby environment, considering how the stellar mass compact object distribute around the massive black hole. And if we observe a number of EMRI, we can also constrain the massive black hole mass function. And so that we have not to rely only on the merger of massive black hole binaries. How do they form? So generally in the galactic center, we have that the density profiles are generally steep, and so we can reach very high densities. And these high densities generally catalyze very strong dynamical interaction that generate a plethora of phenomena, among which we have EMRIs. So the standard formation mechanism is the two-body relaxation channel, in which we have a massive black hole that is surrounded by a cusp of stellar mass compact object. And because of the cumulative interaction, the two-body interaction between all the bodies around the massive black hole, at some point, one of them can be deflected on a very low angular momentum orbit. And this compact object can graze the event horizon of the massive black hole and can be captured in a tightly bound orbit that is driven by gravitational waves. So the system decoupled from the environment. There are no more perturbations that can disturb the gravitational wave spiral. And then the EMRI can finally merge after some time. Of course, this is not only, this is the standard formation mechanism, but there are other processes that can bring EMRIs. So for example, the binary tidal breakup scenario, in which we have a binary of compact objects that, due to the tidal field of the massive black hole, the binary can be separated, and one of the objects can be captured and the other one can be ejected. And finally, we can have another channel in which EMRIs can form in the accretion disk of massive black holes. So in this situation, the viscous torque of the gas there can help in driving the migration of the compact object towards the central object. And differently from the other two channels here, we expect that the eccentricity could be much lower, differently from the standard and the tidal breakup scenario, in which the eccentricity can be quite high. And finally, we can have another possibility. So we can have that EMRI can be formed due to the perturbation of another massive black hole. So we can think about the formation of massive black hole binary because, as we know, the structure of our universe can form in a hierarchical way. And so this means that during the cosmic history, you can have merger of galaxies. And if every galaxy hosts at least one massive black hole, then we can form massive black hole binary. So they can be there. So here we analyze exactly this process in 3 different steps. So the first step was to infer which can be the dynamical formation of this kind of object in the context in which we simulate this kind of system. The second step has been to infer how many of them can be found in the universe, the cosmological rate. And then the last step is how many of them we can actually observe with these. So something slightly similar was considered in the literature, for example, in this paper of William work, but they consider a much more simplified physics, and we found quite some different results from them. And also recently by Nautz and collaborator, we consider a different mass range and a different approach. So this is our initial setup. So we consider a primary massive black hole that is surrounded by a cusp of EMRI, so a cusp of compact object that will be EMRI hopefully. And then we have a secondary massive black hole here that forms a binary with the primary. So we are in a configuration that is called hierarchical triple. So we have an inner binary formed by the primary massive black hole and the stellar mass compact object, and the outer binary that is there, the massive black hole binary. We evolved the system to the post-Newtonian equation of motion, but we also consider the effect on the environment. So we have the stellar potential around the primary black hole in order to meet the fact that there are other objects around it, even if we are considering single triplets in each simulation. And we are also considering the effect of the stellar average. Because of the interaction we start, the massive black hole binary shrink during time. And so the two massive black holes get closer and closer with time. So we consider 3 different masses for the primary massive black hole and selected them in the region when we expect that they could be hopefully observed by LISA. So these 3 range of masses, 3 values of the masses. We then consider 4 values of the mass ratio from 0.1 up to 0.03 and 2 different values of the initial orbital eccentricity of the massive black hole binary. For each of these 24 combinations, we consider, we run 20,000 simulations for a grand total that you can see here. So we found that EMRIs can be generated in essentially 2 different ways. We can have secular interaction because we have at the beginning an hierarchical treatment. And then we can have also chaotic interaction. So in the first stage, the main mechanism that can produce EMRIs is the Lido-Kozai mechanism, in which if the orbital plane of the 2 binaries, the outer and the inner, are sufficiently misaligned, the 2 binaries can start exchange angular momentum, and this exchange generates oscillation between the inclination and the eccentricity of the inner binary. In this plot here, you can observe the relative separation, time evolution of the relative separation of each pair of the bodies. In particular, the orange one is the relative separation between the primary massive black hole binary and the stellar object. That when the spread here means that the eccentricity is growing a lot and the pericenter passage is very small. So this means that eccentricity is growing because of the Lido-Kozai oscillation. However, here we have a complication because the massive black hole binary is actually evolving in time. So the binary is getting tighter and tighter. And at some point, the triplet can lose its hierarchy. And in fact, here, towards the end, we can observe that the situation becomes a bit more messy because the chaotic interactions start to play a relevant role with respect to the second one. And what we have found is that when we have a mass ratio that is particularly high, then secular interaction play a dominant role. While for mass ratio that are much smaller for the massive black hole binary, then chaotic interaction dominates. We can infer this by this histogram on the first line, in which we have the histogram of the initial parameters of all the system that you are simulating. So the one in gray. In green, you can observe the distribution of the parameters of the initial parameters that are then identified as EMRIs. And as you can see here, there are a strong selection around 90 degrees, where the Lido-Kozai oscillation are maximized. So here, the secular interaction play a dominant role in driving the formation of EMRIs. On the contrary, for the low mass ratio case, there is no selection in the orbital inclination. And so this means that chaotic interaction actually play a dominant role. And in fact, what we have found is that low Q, high eccentricity form EMRI through chaotic interaction, while high Q, low massive black hole binary eccentricity generally produce EMRI mainly because of secular interaction. And except for one case, we always find that by lowering the mass ratio, the number of EMRIs generates increase. Essentially because if the perturber is too massive, the perturbation is too strong, and generally the stellar mass Pompadour is the lightest one, gets ejected very quickly because the three-body problem is unstable. And when the mass is so different, the most likely outcome is the ejection of the lighter of the bodies. So we have the number of EMRI formed. We also know how long it takes to form them. We can estimate which is the rate. And we have found that the rate is generally 10 up to 100 times larger than the standard EMRI rate from the two-body relaxation channel. But differently from that rate, this is not a steady state rate, but we have a sort of burst EMRI formation. And this burst is determined by the lifetime of the binary that has a limited lifetime. In fact, the massive black hole binary shrink because of stellar hardening and then because of gravitational wave emission. So at some point, there will be no binary anymore and only a single massive black hole. So here we probed the efficiency of this kind of interaction in forming EMRI. The next step is to infer which is the likelihood of having such kind of system in the universe. And to do this, we coupled our results with a cosmological code, that simulates the cosmological formation of structure. In part, this code is L galaxies, so a semi-analytical model built up on the merger tree of the Millennium 2 simulation, the dark matter only simulation. So this code tracks down the formation of galaxies in the past, and the code can populate each galaxy with a massive black hole, and then we can form a massive black hole binary in the cosmic history. And in particular, for this kind of synthetic universe, we found several mergers of massive black hole binary per year that are distributing the redshift, mass, and mass ratio in this way here that you can observe. We can couple for our efficiency of EMRI formation to these rates here, and what we found is this: that for both the initial value of the orbital eccentricity, we found tens of EMRIs per year from this kind of channel, and they are distributed in this way here according to the redshift, mass, and mass ratio. Of course, the distribution with redshift is very close to the distribution of the massive black hole binary, because our simulation does not depend on the redshift. But there is a clear trend with the mass of the primary of the massive black hole, so an increasing trend of the massive black hole binary. So here we have more EMRIs than here. So these are all the EMRIs in our synthetic universe. Of course, in order to say how many of them can be detected, we need to couple this information with the LISA sensitivity. So we consider a waveform model that is quite simple, the one of Barak and Cutler that we have used also in this work here. So a leading golden waveform. And we assume that EMRIs can be detected when they reach this SNR threshold of 20. And what we have found is that assuming a Fourier of LISA emission, that we have also tens of EMRIs detected. So 10–15% of all EMRIs in our synthetic universe could be detected by LISA, considering this kind of channel. And this is the distribution of the SNR that we have. And this is also the distribution of the masses of the primary and the redshift that we have found. So essentially, LISA is able to detect EMRIs around the smallest mass of our sample here, and that our redshift that is around 0.5 or so. And this led me to my conclusion. So the formation rate of EMRI from the massive black hole binary channel is generally much higher than the standard two-body relaxation channel, but this concentrating in a formation burst of EMRI because of the limited lifetime of binaries, massive black hole binaries. The rate that we have found is much higher than what has been found in the literature, probably because of the more sophisticated physics that we have considered here. And we have a sizable number of EMRIs that could be detected by this kind of channel. And probably we also underestimating these rates because the limited parameter exploration that we have done, because we have surveyed only few values of all the possible parameters that we have. And in fact, we can foresee some improvement of this work. For example, we can explore definitely a wider parameter space in order to understand how the rays can increase. And then we can also refine the physics that we consider. So we can introduce also the effect of the spins in our code, because of course the formation of EMRI is a delicate process that consider how the orbit of the stellar mass compact object grazes the event horizon of the massive black hole. And with spin, we know that the size of the horizon can change. We can also introduce in some way the stochastic kicks that EMRIs are subjected when they are orbiting around the massive black hole, so the interaction with the other compact objects that are there, that here we have neglected, but of course during our simulation we have checked that the time scale of the evolution is below the two-body relaxation time scale in order to safely assume that the system is not perturbed. We can introduce also different stellar potential, and we can also improve the semi-analytical code that simulate the evolution of massive black hole binaries. So we can have a much more reliable rates of massive black hole binary. And finally, we can also find out if there are some specific properties or some peculiarity of the EMRIs that can be formed from this channel in order to be distinguished from those that can be formed from other channels. So thanks a lot.
Thank you very much. If anybody would like to ask a question, please raise your hand. So I was going to ask you about that last point, which is on your slide.
Yes.
Are there things that will allow us to distinguish EMRIs formed through this channel from others? At one point you showed that excess of inclinations near polar, but that was dependent on the mass ratio of the MBH.
Yeah, exactly. So what we have found, so of course here we are neglecting spins, so introducing the spins could change. But what we have found is that there is a slightly preferences of EMRIs that are counter, so the EMRIs are counter-rotating. So there is an excess of objects that are counter-rotating with respect, of course. Here this is a Schwarzschild black hole, so introducing the spin could change a lot, but we have found this. Another possible indication could be the level of the eccentricity that generally for the causality oscillation can be much higher than in the two-body relaxation channel. So maybe if we can observe at the plunge an eccentricity that is, I don't know, above 0.2, maybe this could be a smoking gun for this kind of process. But yeah, this is not something that is completely obvious to me.
Thank you. There's a question in the chat from Vivian Langen, who's asking how you can resolve the small compact object on the Millennium simulation.
No, of course. Okay. So we are not using the Millennium simulation to resolve this kind of system, of course. We are just using the merger tree of the dark matter halos in order to track down the formation of massive black hole binaries. We run then a quite large number of simulations in which we can resolve the dynamics of triplets of massive black hole plus the stellar mass compact object. But we are only using the information from the Millennium just to say how many massive black hole binaries there are in the universe. Just for this.
There was a second part to the question, which was what was the lower mass threshold for the massive black hole binary rate?
Okay, go there. So here in this specific model, essentially the lowest mass is around 10 to the 4 or something, yes, and is essentially due to the seeding mechanism. So I would not trust completely this part here because, of course, there are a lot of uncertainties in how massive black hole forms, and so here it's a matter of assumption. Okay, so yeah, different prescription can produce different mass function at the lowest end.
Thanks. We have a question from Christopher Berry. Go ahead, Christopher.
Hi, thanks for the talk, Matteo. I was wondering, you say in your conclusions that one of the things to do is to survey more of parameter space. And
Yes.
I was wondering what the priorities were. Where do you think is most important to extend?
Yeah, so from the rates that we found, it seems that it's still growing around these masses. And so probably it is worth to explore also this range here, even if, of course, if we go up too much in masses, then LISA will lose sensitivity. But still, probably this could be a good idea in which we have to go. And then, of course, we can also refine more our grid, because we consider 3 values of the masses, 4 values of the mass ratio. Then we can consider a much finer grid in order to smooth these curves here that you can see they are quite edgy.
Cool, thanks.
Thank you very much.
Yeah.
One final question from Elena Rossi, just posted in the chat. Can you make an educated guess on the overall systematic uncertainties from model assumptions on your estimated LISA rates?
Yeah, for sure. One of the biggest assumptions is, well, yeah, it's the waveform model that you're using, that we know that, yeah, it's fine, but not the best that you can find. There are much more sophisticated packages nowadays, but yeah, they are a bit more complicated to run. And so at the end, we stick with the most simplistic one. That is the one of Barak and Cutler. Probably using a more sophisticated waveform can change a bit this number. But yeah, we are confident that the bulk of EMRIs can be identified, even if we have used this waveform here. Of course, probably the SNR threshold could be a bit higher in order to be sure that we detect EMRIs. And so this line will shift a bit on this side. So probably can lower this number here. But maybe if we have underestimated the rates, maybe, and we can run other simulation, we can verify if the rates are intrinsically more high, intrinsically higher. And so maybe this can compensate everything. Yeah, so
Okay, thank you. We should move on to the next talk. So the final talk before the short break is from Jian Chen from the University of Peking, who will be talking about the distortion of gravitational wave signals by astrophysical environments.
Okay. Good evening, everyone from Beijing. I am Xian. I'm a faculty member at Peking University. Thank the organizers to give me this opportunity to present my work. The title of my talk is Distortion of Gravitational Wave Signals by Astrophysical Environments.
Jan,
so let me,
would it be okay if you switched your video, your camera on?
It's
please?
already on.
His camera is on.
Oh, sorry.
Okay, I hope everyone
Sorry,
can see
my
me.
apologies.
Don't worry. So let me just remind you first what LIGO Virgo have detected. They have detected almost about 90 binary black hole mergers, which are shown here by these blue dots. Interestingly, even before the mergers, these black holes, many of them are already 3 to 10 times more massive than the stellar mass black holes we know in the Milky Way in X-ray binaries. So this, of course, raised the interesting question about the origin of these very massive objects. And in the literature, there are a lot of formation scenarios suggested. So when my collaborators and I saw these results, we asked us a quite fundamental question. So how is mass measured in the end? Of course, in gravitational wave, you don't directly see the mass. What you see is this wave signal. It can be characterized by a frequency, amplitude, and the time derivative of frequency. It's chirping, the frequency is increasing with time. So you can do a clever combination of frequency and a frequency dot, get rid of the dependence on the separation of the binary, for example, and then you get a chirp mass. So we all know that. And then you can use the third observable, the amplitude, to further infer the distance. And this is how we measure mass and the distance of gravitational wave sources. But the universe is a bit more complicated than that. The universe is expanding, so there's a cosmological red shift. So what redshift does to a signal is that it redshifts the frequency it also redshifts the frequency dot even more because of time dilation effect. In the end, if you wish to combine the observables to infer a mass, you will find that the mass is no longer the intrinsic chirp mass. It's actually bigger than intrinsic mass by this redshift factor. Unless you know the redshift, otherwise you will always get an overestimated chirp mass. So since I'm trained as astronomer, I know at least two other redshifts, Doppler redshift and a gravitational redshift. So the question I asked to myself was, why haven't LIGO Virgo considered systematically these two redshifts if redshift can indeed boost your measurement of the mass? There's of course a reason. In a standard formation channel, these binaries form in star clusters, disks of galaxies, fields. So they're not moving at very large velocities, and they're not residing in a very deep gravitational potential. So people thought these two effects can be safely neglected. But this understanding is incomplete. In the past few years, there have been a lot of works suggesting that in the accretion disks of AGNs, very close to supermassive black holes, you can also form binary black holes. The merger rate is a bit uncertain, as you can see here, but in some models, the rate is comparable to the LIGO Virgo detection rate. So if these binaries form indeed very close to a supermassive black hole, then neither Doppler redshift nor gravitational redshift can be disregarded, right? So you will see that there will be extra contribution in this redshift factor to boost your measured mass and boost your measured distance. So we did a simple calculation back then, just to put a binary close to a supermassive black hole, a curved black hole. So if the gravitational wave from the merging binary come out of the source in the same direction of its orbital velocity, the wave first will be blue shifted. If the wave come out in the opposite direction, the wave will first be red shifted. But these waves all have to climb out of the potential of the supermassive black hole. So in the end, the gravitational redshift will make the distant waves more redshifted than blue shifted. And the magnitude of this redshift can be a factor of 2 to 10 depending on the distance. So the question is, can you really deliver black holes or stellar mass black hole binaries to the last few structural radii of a supermassive black hole? The answer is yes. If you look at the accretion disk, it's not infinitely thin, it's supported by gas pressure. Most of the disks are hotter inside, cooler outside, so there's a pressure gradient pointing outward in the same direction of centrifugal force against the gravity. For this reason, gas in the accretion disk, at least the outer part of the disk, are rotating slower than Keplerian velocity. On the other hand, small bodies embedded in a disk like a black hole will not feel as much the pressure, so they are still rotating at a Keplerian velocity. So you see that black holes are moving faster than the gas. Then black holes will feel effectively friction and they will migrate inward. Then there's no problem for them to migrate to the vicinity of the supermassive black hole. And then the question is kind of a reversed. The real question is, can you stop them, these small black holes, from falling into the central supermassive black hole? Otherwise, they will just fall into the black hole one by one. You never have the chance of forming a binary. The answer is again, yes. Especially when the accretion rate onto the supermassive black hole is very high, then you will have an inner part of the disk. You can see that this is a log in unit of a Schwarzschild radius. So this is inside 10 Schwarzschild radius. There's a region where the gas is actually rotating super Keplerian. This phenomena is known for a while. In the 1970s, people already pointed this out. This is a consequence of a combination of GR and the fast advection of momentum into the central supermassive black hole. So anyway, in this case, this is the equipotential, and this is where the potential is the deepest and also the pressure the highest. Inward, there's a pressure gradient. It's pointing towards a black hole, okay, in the same direction of gravity against centrifugal force. So in this part of the disk, gas actually are rotating faster than Keplerian velocity. So they are giving angular momentum to the stellar mass black holes here, if they are stellar mass black holes here. On the other hand, the stellar mass black holes orbiting around the supermassive black hole will lose angular momentum due to gravitational wave radiation. So the gain and the loss of angular momentum will balance somewhere, and which has already been pointed out in the 1994 paper. And you can see that no matter where you put the small stellar black hole, they will all migrate to a place almost at the east coast. This is also in unit of the structural radii. Okay, so we adopted this model and we try to predict where this trapping radius is, and this is the result. Just to guide your eye, this is a total mass of the binary stellar mass black hole. So 10 solar mass black hole is here. Say 20 solar mass black hole in total is here. And this is a mass of the supermass black hole, 10 to the 8 solar mass black hole is here. We see that in a large parameter space, there is indeed this trap, and these numbers indicate their radius in unit of the structural radii. Okay, so in general, your black hole had better to be very massive, and the accretion rate, of course, has better to be high, close to the Eddington rate. In other part of the parameter space, you don't have this trap anymore because small black holes will be flushed into the supermassive black hole very quickly. So from this, we can infer that maybe in the most luminous quasars, you will have this kind of a migration trap. Since there's no more migration trap further inside, we call it the last migration trap. And you can do a simple population synthesis model and predict the rate. This is the result. Anyway, this accounts for about 2% of all the LIGO Virgo events. This may seem to be a small number to you, but don't forget, LIGO Virgo have detected almost 100 binary black hole mergers. So maybe a couple of them is coming from this channel. Interestingly, this source, GW 190521, is one of the most massive binary black hole mergers detected so far. 30 days after the gravitational wave event, there's a AGN in the same sky area just flared out. Okay, so that's why people suggest that maybe this AGN flaring is associated with a gravitational wave source. But interestingly, if you look at the gravitational wave luminosity distance measured from the chirp signal, you see that the distance is 4.5 gigaparsec. And the AGN, by measuring the broad line, you can infer that the luminosity distance is 2.2. So there's a factor of 2 difference here. And then many people take this difference as evidence that the gravitational wave is not associated with the AGN. But in our model, this discrepancy is kind of expected. This is caused by Doppler and the gravitational red shift because the merger is close to a supermassive black hole. I think this is very interesting, and in the future, LIGO and Virgo will certainly detect more such events. Can we distinguish such thing? So since this is an EMRI session, many of you may have already recognized that this is an EMRI. Okay, but the small body now is not a single black hole, but a binary stellar mass black hole. Modeling such a system, especially its dynamics, is very complicated. Each of the black hole is moving very fast around the supermassive black hole. Don't forget, we are dealing with a system at a few gravitational radii. So the velocity around the supermassive black hole is close to the speed of light. So post-Newtonian formalism will certainly break down here. Full numerical relativity is also formidable because if you compare the size of the binary and the background curvature radius, you will see the dynamical range is too large, million to 10 million. So it's very difficult to directly simulate this system. However, we can take advantage of the free fall, the idea of free fall. So if you stay in the free fall frame, since we want to use LISA to track this binary, so this binary is maybe a month to years before the merger. If you stay in the free fall frame, at that stage, the two black holes are not moving extremely fast relative to each other. Their velocity is mildly relativistic or even Keplerian. So we can model the binary motion in the free fall frame very well. On the other hand, the binary at this stage is very small compared to the background curvature, which means if you stay in the free fall frame, the space-time is effectively very flat. There's only small perturbation induced by the existence of the supermassive black hole here. But that small perturbation can be treated as a perturbation to the equation motion, which effectively produces this so-called gravito-electromagnetic forces, which can be easily inserted into the equation motion and study the evolution. So the trick is simulate the system in a free fall frame, and this is the result. So without the black hole, of course, the binary will just move on concentric circles like the blue and the orange circles, and they will not move. But because there's a nearby supermassive black hole here, it induces this like electric or magnetic-like forces as is indicated by these arrows and colors. then the binary will start to drift relative to the free fall frame. Now, the black line here is showing you the center of mass. You will see that in the radial direction, there's an oscillation, and in the azimuthal direction, relative to the supermassive black hole, there's a drift. Okay. This is a motion relative to the free fall frame, which means the binary, at least the center of mass, is not following a geodesic. It actually deviates from the geodesic. And don't forget that we put the binary at 3.3 gravitational radii. It's very, very close to the central supermassive black hole. If you put the binary even closer at 2.8 gravitational radii, then the evolution is more irregular. This is closely linked to the fact that the inner binary will soon become very eccentric. The eccentricity is excited by basically a combination of the tidal force and also the gravito-electromagnetic forces. At this large eccentricity, the binary will certainly merge. Here, the binary didn't merge because we haven't put in the PN terms yet. But if you put the PN term, then in many cases, these binaries will merge. Then this produces an interesting coincidence between smaller distance to the black hole and the binary black hole merger. This is a coincidence that we are looking for at the beginning of the talk, right? This will be the redshifted source. And I already mentioned that the center of mass deviates from a geodesic. And in several hours, it deviates this amount, but in 8 days, it will deviate already by 1 radian. So if you are treating the binary as a test particle, then you will be certainly wrong in 8 days. So I think by looking for this deviation, you can also infer whether or not the small body in the EMRI is a single body or a binary. If the binary merges, then the gravitational radiation will take away momentum and cause a merged product to recoil. And this will induce a kick on the merged product. This will produce an interesting glitch in the orbit around the supermassive black hole. And this is also a glitch in the EMRI waveform. Don't forget the orbital motion around the supermassive black hole produces low frequency waves that is basically an EMRI waveform. So this blue curve is the waveform without the kick. Red is where we introduce a kick at time 0. And after about half a day, you can already see by eye that the kick will induce perceivable differences. So this half day is also kind of a time resolution. You need to wait this amount of time to see the difference. Then you can use this difference to infer interesting things like the recoil velocity of the merged product. And look at the accuracy here. Here we induce only a very small recoil velocity, 10 kilometers per second, which is certainly much smaller than what will happen in the real universe. And you can reach an accuracy of 1% to measure this recoil velocity. You can also measure how much mass is taken away by the merger of the 2 black holes. Gravitational radiation takes away rest mass, and the accuracy can be 2%. The point is that these constraints are 10 times better than the current constraint put by LIGO-Virgo by measuring the merger wind-down waveform, for example. Another interesting test of fundamental physics is test of the dispersion collision.
You've got 2 minutes left, please.
Sure, I'm almost done. Okay. So the merger of the binary produces high frequency wave, and its orbit around the supermassive black hole produces low frequency wave. In some massive graviton models, these waves are traveling at different times. So you can look at the arrival time of the merger signal, like a LIGO-Virgo signal or a glitch in the EMRI, and look for this time delay. Say if you don't see delay, then it means that the delay is smaller than half a day, the resolution I talked about in the last slide. And you can use this to constrain the mass of the graviton. For example, in this case, you can constrain the Compton wavelengths of your graviton to this level. Compared to the constraint currently done by LIGO-Virgo, using this kind of binary EMRI, you can achieve a 10 times better constraint on the graviton mass. So a short conclusion, I wanted to say this source is interesting, but now I realize it's also a mess because the dynamics is very rich. So it also indicates that the waveform is extremely complicated to model. I do think some model independent algorithm is needed to extract this signal finally out of the LISA data stream. Thank you all.
Thank you very much. If anybody has questions, please raise your hand. I see there is one from Christian. Please go ahead.
Hi, thanks. That was a very interesting talk. So I had a question about the fact that you said that you could determine the by looking at the dephasing. I think it's 1 in 8 days that you could tell if it was a binary. So I'm always wary with these arguments because there are many different sources of dephasing. So I was wondering if there's anything specific to this situation where you would know that this dephasing is to do with it being a binary, or if this is going to be degenerate with other astrophysics.
Right. Of course, this is still a working in progress. We're trying to find the distinctive signature, but I want to point out there are two kinds of dephasing. One is due to the kick and the recoil. You see the dephasing here by eye. Another dephasing is here. This is due to the fact that you have some internal structure of your small body that also introduces a dephasing. Whether this will degenerate with some other effects, for example, nearby gas or some dark matter cusps or something, we are working on it. So I would not say, I don't have a conclusion yet, let's say. I think in some parameter space, we do think we can distinguish these or did sort of break the degeneracies, but there are cases we do see a very strong degeneracy.
Okay, thanks.
I don't see any more questions from the room for the moment, but can you say a bit more about GW 1905-21? You said that the factor of 2 distance discrepancy could be explained by these effects. If you assume that this is the explanation, how close was the object to the central black hole?
So this is a factor of 2. If the central black hole is a Schwarzschild, it's at the east goal. If the central supermassive black hole is a curl, then it's even further away from the east goal. It doesn't have to be that extreme. Like 2 times the east goal is already fine.
I see. Okay. And in the binary EMRI case, if we assume that LISA is operating concurrently with 3G detectors, presumably the gravitational waves in the binary would themselves be detectable by ground-based detectors. So this is a potential multi-band source?
Yes, indeed. It's a multi-band really at the same time. You see them at not like wait 3 months to see the event turning up in like, no, you see them at the same time. I see that Stas has a raised hand.
Yeah, go ahead, Stas.
Excellent. I have a question about exactly on this. It's about last migration trap. So as far as I know, last migration trap is usually a few hundred Schwarzschild radio, gravitational radii, and you are talking about really close to the last stable orbit. How do you bring it from the trap where you want them to kind of form to the very end?
It's a different mechanism. So the usual migration trap you see is basically somewhere here due to the discontinuities in the accretion disk. But our migration trap is caused by first fast accretion, and then you have this super Keplerian rotating region. And this will give angular momentum to stellar mass black holes. And the loss of momentum due to gravitational wave radiation will keep the balance in the end. Well, you can look into more detail in this paper.
Okay,
the final trap is. So it's different from the standard migration trap.
Okay, thank you very much. I don't see any more questions, so we'll move to our short break. We're slightly over time, not very much. So we'll come back at 4:20 and have the last 3 talks then. Thanks to all our speakers from this first part of the session.